I gotta. The TA made a couple mistakes. I want those fixed. When the homework will get back to you, I've got to get in touch with the grader. But I'll try and have them available on Monday, right? And then the tests on Wednesday. But as of now, did people get back homework 5 yet or no? I think homework 5 went around, right? Okay. Okay, yeah. So it's homework 6 and 7. So the solutions for 6 are already online. Solutions for 7 today or by tomorrow. And then the homeworks to be returned when I track down the grader. Okay, so the way this will work is you ask questions, any question you want. I mean, you know, if it's a question, you can even ask questions of what's on the final because I don't know yet. I haven't made up the final yet. So it's easy to answer, I don't know. But anything about any of the homeworks, any questions you have on the material, I'll try to answer. Yeah?
Can you go with leaky bucket?
Leaky bucket, yeah. Okay. Yeah, the way it was written up in the homework, it was a little bit confusing. So let me talk about the way leaky buckets should be, because you have packets going through a router, right? And the bucket itself is not the packets. The bucket contains tokens that can be used with the packet. Okay, so the router itself could have a huge buffer and can store lots and lots of packets, and the bucket can be a lot smaller, storing fewer tokens than the number of packets that the router can store. Okay, so the bucket has some bucket size B, and then some rate. I don't know if you use R or rho. Okay, and the idea is that every 1 over rho seconds, okay, or it can be exponentially distributed. So just the rate is rho. So on average, every 1 over rho seconds, a token is placed in the bucket. Okay. The router is only allowed to send a packet if there are tokens in the bucket, and every time it sends a packet out, it uses one of the tokens. Okay? So if you've got 3 tokens sitting in the bucket, and all of a sudden 5 packets arrive at the router, okay, then you know, let's say 5 packets come in. Then immediately you can send 3 of them out, right, and you get rid of your 3 tokens in the bucket. And then these other 2, they have to wait for the next 2 tokens to be dropped in. Right? The next time a token gets dropped in, the next packet can be sent, and the token's gone. The next time a token drops in the bucket, packet sent, and it can be gone. Yeah, Patrick.
The bucket's at the router, or the bucket at the computer sending?
The bucket. Okay, the bucket. I mean, you really put the bucket anywhere you want. Right? The notion is leaky bucket flow control. So somewhere or everywhere, you're going to have this pacing mechanism, right? So where you put it isn't as important. It's just how the mechanism is implemented. So in the homework, the idea was, suppose I've got a series of routers. And suppose each of them implements its own leaky bucket mechanism with bucket size BI and rate rho I. So I guess B1, rho 1, B2, rho 2, B3, rho 3. Right? And then the question was, the question was poorly posed because it talked about packets being lost if there's not. It sort of implied that packets were being placed into the bucket. Okay. So I'm going to have the grader grade it rather flexibly. But the idea was that you're sending some packets through these routers, okay? And you've got this leaky bucket mechanism implemented in each router, okay? So what's the biggest burst that could possibly come out at the other end? It turns out that the biggest burst is going to be the minimum over all these bucket sizes. Yeah.
fine.
But isn't a flow control implemented between a sender and a receiver? So each of those routers along the way have buckets.
So usually you would not implement the way it's used in practice. Usually there's some gateway where the leaky bucket mechanism is implemented. Okay, but you could imagine I could install it at every router. It's possible. I mean, you may not ever want to do it in practice, but it's possible. Okay, maybe each router wants to limit the rate at which it sends out the packets that it has. Maybe it always wants to avoid sending out a burst of packets that's too big. And a leaky bucket mechanism is the way to do that.
So one bucket, maybe the last router wants to give a bucket back, give a token back, it copies it, everyone takes it and passes it on, and that's everyone getting another token?
Every router has its own leaky bucket mechanism built in. So every router has this bucket size B sub I, and it's putting tokens into its own bucket. There's no sharing of buckets or tokens. Okay, and this router can only if it gets a packet, it can only forward it when it's got a token in its bucket. Right. So if you want to look at a burst, what size burst is going to go from here all the way to the end? Okay, obviously the burst has to be able to fit with the number of packets in that burst has to be smaller or equal to the number of tokens that can reside in any bucket. So if you let all these buckets fill up and then sent a burst of packets, obviously the burst that would come out the other end is equivalent to the smallest bucket size, because the router with that smallest bucket would use up all the tokens trying to forward that burst, and the rest of the packets would be delayed. Yeah.
I thought what you're saying is that if the router can handle its queue, like you take upon queue and also process one, wouldn't it be min of the bucket plus one because you also process without losing that?
Yeah.
So if I send a burst of like 6 and I got a queue of 5, it would take all 6 for the first one immediately processed. While the other 5 would put it in queue.
I mean, the argument is, as long as you made the observation about the minimum, that's the important thing. So whether or not you're off by 1, that's not a big deal. But yeah, so you could have an instance where right when you choose to send the burst, another token comes in the bucket, right? Like it just happens to be at the exact same instant in time. You get +1. I mean, the odds of it happening are so small that you generally just ignore that.
If the next is the router in front of you has
So the problem with the problem with the way the homework problem was specified was that it was implied that there was some implication that the bucket size was equivalent to the buffer size in the router. That didn't. The question I wanted to ask was: assume you have a router with infinite buffer, and then you've got the buckets that are limiting the rate at which the router can send packets forward. And when I wrote up the problem, that was not made clear, and it was easy to misunderstand or it was easy to understand the problem to mean that the size of the router's buffer equals the size of the token bucket. Yeah.
So you would never actually lose packets because they would just be put in the buffer.
That's the question I wanted to ask. Yeah. But someone pointed out, I forget who, when you read the question, I think it was Ari. When you read the question, it actually says, I meant to say, I think it says lose a packet. At some point it says you lose packets. Actually, I have it here. So, yeah. Give an example of a transmission sequence that leads to a packet loss when the leaky bucket is configured using. So for part A, in part A, I said so the packet is never lost. I didn't write up the question clearly enough. I mean even I got confused between tokens and packet tokens in the bucket and packets in the router when I was writing up the problem, and in my mind I had it conceptually separate, and I didn't write up the question well. So if you could have packets being lost, does that change things? I mean, I still think the burst size will stay the same, but what doesn't stay the same is the result that the long-term rate at which packets proceed through the router, the long-term rate should equal the minimum of all these rates, right? If packets never got lost, you can sort of imagine that the slowest point in the process will control the rate at which packets move out through the end. And people ran into trouble when they used this loss model instead of the info queuing model, that if you were before the slowest bucket, you know, if packets arrived bursts, they could get lost. You get big gaps where you should have these big gaps. I mean, it just made the problem a lot harder. So.
Yeah.
Is the burst time synchronous?
The burst.
Or is B1 smaller than B2, but if it's burst on B1, then...
So
If B1 is smaller than B2, then you'll never get a burst of tokens to this bucket of size larger than B1. Right? The biggest burst this router can send out is of size B1.
But then when B2 gives the burst, it's going to be bigger than the minimum of B1. With B2...
If B2's bucket, let's see. So if row 1 is bigger than row 2, okay, then B2's bucket can sorry. If okay, let's just look at two nodes adjacent to one another, and let's look at all the different possibilities of B1, B2, row 1, and row 2, right? So this bucket is of size B1, R1, or row 1. Okay, and this bucket is of size B2 with rate row 2. Okay, so suppose B1 is less than B2, row 1 is less than row 2. That's the first case to consider, right? So the first bucket is smaller. So now imagine I send in a huge burst of packets, okay? This bucket can have at most B1 tokens. So simultaneously, at most, B1 tokens will ever proceed to the next router or the next bucket, right? So the biggest burst in this case, you could have a burst of size B1 coming out. But it can't be bigger than B1. If you send a burst of B2 in that's bigger, right, only B1 of that's going to flow through. That's it. Okay? And then you also think about, well, what if, I mean, maybe the packet somehow gets stuck here and then the other packets catch up, you know, if there are no tokens in the bucket. But again, that doesn't matter, right? So the question is, can you send is there a way to get a burst bigger than B1 out of this? Is there a way to get more than B1 packets into this router? And if you think about it, there's no way to do it. Right? If you want to get B1 packets in more than B1 packets in simultaneously, you can't do it by sending them in, right? Because this will only let B1 through. Right? So the only other way to do it is to let packets build up in this router over time. Right? But why would they ever build up in time over here? They would only build up if the pacing mechanism here was too slow. Right? But if you're using the pacing mechanism, then you're not emptying the bucket. You're only using this pacing mechanism when the bucket is empty. People get what I'm saying? So you can't possibly have a burst bigger than the smallest B sub I. Okay? And similarly, the long-term rate can't be bigger than the smallest row sub I. Right? There's some bucket that's only releasing tokens at a very slow rate. So if you think about it in the long term, you can't beat that rate. The rate at which things move down a chain is always limited by the slowest component. Right? It doesn't matter how fast the other components are on the other sides. In the end, in the long term, this slow link, the packets are going to build up. And when the packets are building up, the token bucket has to be empty. Right? Because if the token bucket had tokens in it, this router would send those packets out right away and use those tokens. So, I mean, you don't even really need to consider all different cases. If B, I mean, we just sort of argued through them all already. B2 is greater than B1. And row 1 is less than row 2. It's the same thing again. I mean, again, if you try to push a burst through here, now it's going to be constrained by, I wrote the same thing. B2 is less than B1. Okay, now it's going to be constrained by B2. Even if you have a very large burst coming through here, this will never let out a burst bigger than B2. Right? There's no way to push a burst out of here bigger than B2. And the long-term rate, again, you're always just constrained by the slowest bucket. Yeah, George.
So are we assuming this packets are never lost in this thing?
So that's what I meant to ask in the homework question. Unfortunately, it didn't come off sounding that way. So.
Part B, though, like, you want an example of a transmission signal that these are packet lost.
Right. So yeah. Right. So the problem with the way the problem was described is that packets and tokens sort of become synonymous. And they shouldn't be. The tokens are limiting the more tokens you have, the more packets you can send through. And the idea was not to, if you're not sending stuff, if you're sending stuff too fast, you're going to start to lose. It's just you looking at it from the perspective where packets can get lost. The problem really just doesn't make sense. So if people had a hard time with it, that's probably why. If you use the packets as tokens, let's say, which is sort of what you have to do when you're talking about the loss, then you're not really implementing leaky bucket. You just have a router that can hold a certain number of packets and can send them forward at a certain rate. And so the question is, give an example of a transmission sequence that leads to packet loss when leaky bucket is figured using rho prime beta prime, where rho prime equals rho and beta prime is greater than B. And the idea here is that right, just a two-router sequence where the first one is what, rho prime equals rho. So both of these routers, the idea was they could process at the same rate. And this guy had a bigger queue, right? Packet loss.
The B1 and B, or what is on the B1?
Sorry?
The B prime is for the second.
Oh, okay. Right. So it leads to packet loss. So leak by figure using B prime B. B prime greater than B. And B, you're saying B prime came out in the second half? That's clear?
So, you need to be a lot of B supposed to be.
Let's put B prime is greater than B, so put B prime in front, right? Yes, Oscar.
B and B prime are not the first sizes of the routers, but B and B prime are the first size of the flow. In that.
Yeah, that's
Where does it say that? Oh, I see. Assumed flow has reserved access to router resources. What is the leaky bucket configuration? No beta. So should use. Oh, I see. Oh. Oh, jeez. Sorry. This is a question from an old homework. So I didn't look at it carefully this year. So now I'm thinking it actually is all correct. I was just misunderstanding the probable time. So you have these routers, they have these processing rates, and then you've got a leaky bucket configuration. You want to make sure you don't exceed the router capacity. Okay. Okay. So the router can handle stuff at a rate. There's a buffer size of BI and can process stuff at a rate of rho I, right? And you want to constrain the rate at which your flow injects traffic in the network, right? And the assumption that's not clear is Yeah. Okay. Right. Okay. Yeah. Packets are going to come in. The router's going to process them at a rate of rho I, and it can buffer up to BI. Right. So even if you send a burst of packets to this router, it's going to process them one at a time and spread them out with rate rho I. Right. They don't go through the router right away. Okay.
And I thought the router is processed back. Lambda I.
Lambda I, sorry. Yes. And I said BI packets. Okay. Now you've got a bunch of these B1 lambda 1, B2 lambda 2, B3 lambda 3. Okay. And now you've got a flow. You've got to limit the rate of the flow such that you don't want any loss, right? Okay. So clearly the rate of the flow has to be less than the minimum of all these rates, right? Rho, so F is going to have rate rho and bucket size, let's call it capital B. Okay? Rho has to be less than less than or equal to the min of lambda 1, lambda 2, or of all lambda I in the general problem. Right? Otherwise, I'm going to be sending packets at a rate that's faster than any router can handle. Right? So obviously some router will overflow and packets will be lost. Okay. Now what can you say about the bucket size of leaky bucket mechanism implemented here? So the bucket size should be the minimum of all these. And why is that? Okay. Obviously, the bucket size has to be less than B1, right? Because if I sent more than B1 packets to this first router, the first router would overflow. Okay. So it's got to be less than B1. But suppose there's some B sub I back here that's also smaller than it. Okay. Well, packets are coming out of here at a maximum rate of lambda 1. Okay. All right. So actually, I don't think it's just me. Let's see. So let router J be behind router I. Okay, so I is less than J. Okay. Suppose lambda I is less than lambda J. Okay, so the router in front has a slower rate. Then packets should never fill up in this router's buffer, right? If this guy has a slower rate, then the fastest at which packets can arrive to this router is constrained by that lambda sub I. Right? So its bucket will never fill up. So packets never queue up. At router J, right? So router J's bucket size does not matter. Right? Okay. Now, if lambda I is greater than lambda J, for all for all the ones in front. Okay. Well, now potentially these can all send at a rate that's faster than what my router can handle. Right? Maybe it's not an interesting problem. Yeah, so as long as the rate's already been constrained, so it doesn't go faster than the minimum rate, the bucket won't fill up. So the problem with the way the problem is specified is, if you assume when a burst arrives in a router, yeah. So I'm going back. The problem, I do have a problem with the problem, but it's not the same problem I had before. But the problem is, if you assume that the router automatically starts placing packets, we're not really making use of the bucket. So what would be the right way to ask the problem? Okay, here's the change you have to make. Yeah. Instead of deterministic rate lambda, suppose processing times are exponentially distributed. Now, you know what? Forget it. It's a stupid question. Never mind. I'm not even gonna have the guy grade it. So forget that question. All right. Understand leaky bucket. Okay. And understand that for leaky bucket, that the tokens and packs are two separate things. Okay. And the tokens are controlling the rate at which packets can flow through a router or some sort of gateway. It's just a gate, right? Like a bouncer at a bar. Okay. It's a bouncer at a bar, right? And you can tell the bouncer, like, so there's like the big bouncer, right? They usually kind of look like that. And then there's the little guy who's sort of the brains of the operation, who tells the bouncer, when to let more people through, right? So the little guy comes out and says, okay, you can let another one in. Okay, you can let another one in. Okay, you can let another one in. Right? And as long as there's someone there, the bouncer keeps letting them through. And if there's nobody there, the bouncer sort of keeps track of, okay, I can let up to 4 people through. Right? Because this little guy told me I could let people through, and there's nobody standing on line. So if 4 people show up, I can let them all in at once. Right? And then there's just some cap. The bouncer, he's not that bright, so he can only count up to 8 or something like that. So when the little guy says, let more people through, once he gets 8, after 8 people, the bouncer just, that's all I'm letting through, and just sort of forgets. Beyond that, and when people come, if it's a group of, however many he's gotten his tokens here, that number can go through, and he gives out the tokens. Or even better, the little guy gives him, passes or something, like, give this to the people when they come in, and he can only hold like 8 at a time. And so when he gives them another one, he like drops it and loses it. And they're made out of glass, so they fall and they break. And so that's sort of what it's like. He's a big guy. Intimidation. Yeah.
So once again, is the queue independent of the number of tokens and the rate?
So, all right. So what if I was going to ask a question with routers and leaky bucket? That would make sense. I don't know what I'd do. I have to think about it. But if I think about if I come up with a question, the important concept will be the leaky bucket part. So let's see. Right. Oh, they wait in the queue. Right. Nobody gets thrown out. They just have to stand there and wait. Queue length can grow to the end.
We can have a restriction on the queue.
Sorry.
Can we have a restriction on the queue length?
Can you have a restriction on the queue length? Sure. And you're asking what kind of question did you ask?
No. In that case, the maximum number of people that can go in will depend both on the length of the queue and the number of tokens.
Well, again, it depends how you phrase things. So it's always bounded by the number of tokens, right? But suppose I've got a queue length of 3 and 20 tokens, a bucket size of 20 tokens. So presumably, if 20 people show up, right, none of them have to wait on the queue. They go in right away. Or you could say that when they line up, they have to line up at the queue, and then the gate is open, and they could be dropped at that point in time. You could pose it either way, right? and you can imagine a system working either way.
So in that case, packets would be lost if the queue is full.
Well, okay, what I'm saying is, suppose you have a queue with a buffer of 3. I'm implementing a leaky bucket mechanism. And suppose there's no processing delay whatsoever. Let's take a case where there's zero. If there's processing delay, then yeah, you're going to queue up 3 packets, and the rest are going to get lost. But if there's no processing delay, then when I have my 4 or 5 or whatever, if it's smaller than the bucket, they can all go right through, right? And if I've got this leaky bucket mechanism sort of pacing things, 20 of them can go through, and then I'll be out of tokens, and then they'll start queuing up, and then beyond 3 of them, they'll start getting dropped. Okay? So in that variant of the model, if you assume that basically you don't have a processor here. If you can't. I was trying to mix the idea of having a processor there and leaky bucket, and it really doesn't work well. So forget that. I'm not gonna try to mix the two together. It just didn't work. Yeah, George.
Can you explain poison reverse when you get to infinity? Count to infinity.
Okay.
Sure.
Any other questions on leaky bucket?
Okay.
Count to infinity. You never actually get to infinity. You get the maximum value. But the problem is that they call it count to infinity because you get up there very slowly, right? So you don't actually get to infinity. But you're asking, why does it happen? Yeah, why does it happen? So the problem always happens. It'll only happen when you have a graph. And some edge that had weight A goes to weight B, where B is greater than A. If the edge weights shrink, the problem doesn't happen. The problem always happens when things grow, or if an edge that was there disappears. Right? That's equivalent to an edge disappearing is equivalent of the weight going to infinity. You never want to take that edge. So why does it happen? Well, again, it happens because, for instance, if you're not using poison reverse, okay, then suppose this guy, to get to some destination, this guy wants to go that way. This is some node A and this is some node B. And to get to that destination, B decides it's going to go through A. Okay. So, not poison reverse. A has some distance D. B has some distance delta to get to A, right? And maybe B has some alternate path of distance D prime that also takes it to the destination. Okay, let me draw these as squigglies just to indicate there could be several hops. Right? So B is reporting to A that it can get to this destination in distance D plus delta. Okay? And A is assuming when A hears that B can get there in distance D plus delta, A doesn't know that B is planning to go through it. Right? All it knows is it's got this distance D plus delta. So suddenly this changes. It gets really long. Right? Well, A looks at this distance is no longer as good as what B was claiming it could do. Right? B was claiming it could go D plus delta. And compared to something that's much, much larger than D plus delta is pretty good. Right? So now A is, instead of A choosing to go this way, A is going to turn around and point to B. Right? And add delta to the distance that B was reporting. So A can now get there in distance D plus 2 delta. Okay? Because B was going through A, and A has now changed its distance, B has to adjust its distance as well. Its distance is now A plus 2 delta plus this additional delta. So B's distance is D plus 3 delta. And then A has to adjust again. And they go back and forth. The problem is that they're pointing at one another, and they're not really realizing it. Okay? At some point, this keeps growing and growing and growing until finally either d prime plus delta, or finally d prime is less than this, this count grows above that. It's either, eventually it's going to grow above this distance or this distance. And one of the two is going to change the direction that it points. And at that point, everything will stabilize again, right? Whichever one is shorter. Or they could both actually, B point toward D prime and A could point toward D, depending on what is the shortest path. I mean, it'll resync on the shortest path. Yeah, Ezra.
You have another node that's connected with A and B, and then you know that C changes to a much larger value. So then A won't report to B because A's shortest path is never going to do B. But when C reports to B,
you have A and B. They're connected by an edge.
A, B, and C.
And C, like a triangle.
Like this? Okay.
And
How would it pass to B?
I mean, C has a. Is it like this? I mean, there's this path and this path and that path.
Yeah, something like that.
Okay.
So the point is that when A's initial path changes, it's not going to report to B.
Now you're using poison reverse or not? Using poison reverse.
So it's not going to report to B because now the shortest path.
So A was initially going this way. Yeah? Or how?
Yeah, let's say A was initially going that way.
Or it could also be taking this path. I mean,
Let's say it was going that way.
top or to C?
Through C.
Okay, A is going this way. B is going through A? Or
B is going by itself.
directly? Okay. And C, or do we not care about C? Or is C going directly also?
Okay. I'll email you later about it. There was some problems I came up with. I'll email you.
Okay.
I have a question about something else.
Any other questions on distance vector poison reverse?
Where's that point?
Oh, we never got to it, but going back to this example, if poison reverse basically says if you're choosing to take the path through a node as your shortest path, then you don't report your distance to the destination to that node. If I'm going through you, rather than tell you I can get there in distance 12, such that if the path that you're taking fails, you may decide that 12 is the best route for you. You may turn and go through me, at which point we're pointing through one another. That leads to this count to infinity problem. It's better that if I'm going through you, I just tell you, look, my distance to that destination is infinity. I'm going through you, so what do you care what my distance is? You don't want to go through me because my distance is definitely farther than you. And it's not until I change, if for some reason your path gets really big, when you send me that information using poison reverse, I might choose to go another way. At which point then I'll be reporting my shortest path information to you. But I mean the way to see this provably that it's correct or that it won't cause an inconsistency is that you should never have to report. It should never be the case that the two nodes are taking each other as the first hop to some destination, right? So it's always okay that one of them report distance of infinity, the one that's further away. There's no harm in reporting distance of infinity to the one that's closer.
What if the path going to a destination just all of a sudden lost?
The links are gone.
Yeah, the link's gone. Then A still think they can get to the destination going through each other.
I mean, you're saying the links are suddenly gone without poison reverse?
Well, yeah,
Without poison reverse, sure. It would be the same as this point to infinity. Yeah, you still have the poison reverse, the count infinity problem.
Yeah.
But in this example, if you implemented poison reverse, right? So B would be pointing toward A, and initially it would be reporting infinity, not delta plus D, right? So when this link fails, okay, A loses the ability to reach the destination as far as it knows. It has a path of infinity this way and a path of infinity that way. A just says, I can't get there. At which point B will choose to go this way, right? At which point now B is poison reversing in this direction and it notified A.
that's also the D prime.
This is also lost?
Yeah.
Then there's no path.
Thinking like
Yeah, they both, my distance is infinity. My distance is infinity. Well, you know, we can't get there. You've got infinity, but that's the correct answer. You can't get there. So. Yeah, Patrick.
Poison reverse. Thank you. If A and B, you're using poison reverse, and then the A's destination disappears, and what will it do then? How does that start? How does the node start in sequence to therefore determine that it now has to go to B?
Oh, well. You're saying in the context of the table. If you're looking at it from the perspective of a table.
How therefore the update?
Oh, I always the rule is simple. I look at my table, and whenever I keep track of the shortest path vector to all destinations, right? And if ever there's a change in the network, and I have to make updates to my table, I recompute this minimum distance vector. And if any component changes, I send that out to my neighbors with the modification for the Poisson reverse. And if nothing changes, I don't send anything out.
So A now changes. A says I have an infinity destination, sends it to a neighbor B.
Yeah.
B says, well, that sucks. Whatever. He doesn't make any updates to his table.
No, it does. B says B's table would look like this. B, here's B's table. Here's some destination D, and it's got a neighbor A and a neighbor C, right? And let's say A's distance is 5 and C's distance is 7. So it's going to choose to go through A. Sorry, I drew the table backwards from how I usually draw it. Here's the destination. Here are two of its neighbors, 5 and 5 is the shorter path. Right? So in this case, if it's going to send out a vector, it's going to send out the vector 5. Or infinity if it's Poisson reversing. In this case, it would say send infinity to A and 5 to C. Right? Now, suppose that A's distance suddenly grows. So A can no longer send 5 to B. A now has to send, 1,000. Right? Its distance to destination is 1,000. So B looks at this and says, all right, my shortest path is now distance 7. And that was a change in the table. So now it sends it to, in this case, now it sends it to A and it Poisson reverses C. So, in fact, if the distance stayed the same, but the neighbor who you chose to go through changed, you should also send out the message when you're using Poisson reverse. Right? I was Poisson reversing this guy with this, and this guy was telling distance 5. If I switch direction, I should be telling this guy. I said Poisson reversing this guy and this guy distance 5. Now I should be telling this guy distance 5, and this guy should be Poisson reversing. For the case, and the example I was just talking about now was suppose they're both the same distance. You got to pick one or the other. So I can pick C, and I should Poisson reverse C, and I should send the information to A. And now if this link suddenly fails or grows, this becomes 7. Well, now I want to choose A. And even though my minimum distance vector didn't change, I switched who I was Poisson reversed to. So I should still. I should just change who I'm sending the message.
So if your table doesn't change, except if your table doesn't change in terms of distance, but the distance that you sent out to A, or the distance vector you send to A changes, would you still send out to A?
So here's a real simple change you can make. The problem is it's only a problem when the two are tied. Okay, so make them small, make them different by a very, very small amount. Right, now they're slightly different values. So now if I had to change, I would change from 5.00001 to 5.0000001. And so if the value changes, even by that small amount, I should re-forward the message.
Just trying to think of, I ran into a problem, and I just can't think of what it was, where he didn't have to update its minimum vector table, but A needed to know that it no longer went through. B no longer went through A.
That was it, when they were both the same.
No one could hold it. And he still sent that.
Yeah, you should. Right. If they have the same value, that's the one case when you're not implementing poison reverse, it doesn't matter because you're still sending out the same information. But when you are implementing poison reverse, even if the values stay the same, who choosing to poison reverse changes. So you have to. What you should really look for, if you don't want to do this at a very small amount, is are the values the same and is who I'm poison reversing the same? And if either of those change, then you should resend the message. So.
Can we go over that question you changed from homework? Yeah, I think it was 7, where homework question 2. Can we just go over B?
The upper and lower bounds?
Yeah.
Yeah, okay. Okay, so you have two nodes communicating using go back N. So this is homework 7. Number 2. S and R communicate using go back N. And the only special detail is S sends a window of packets. R sends an ACK for the entire window. Round by round. Okay? And for part A, you're told the packets get lost with probability P. Oh, part A, ACKs are never lost. Compute the expected number of packets accepted by the receiver each time. Oh, ACKs are never lost. And same as problem 1. Okay, packets are lost probability P. Okay, so part A is expected number of packets received in a round. Okay, so the easiest way to solve this problem is to find an indicated random variable xi, where xi equals 1 if the ith packet in the window is received. Okay, otherwise it's 0. Right? And you want to compute E of the sum from I equals 1 to W of xi, which is just going to be the sum from I equals 1 to W of E of xi, which is just the sum from I equals 1 to W probability xi equals 1. Right? Receive packet I if and only if you receive packet through part A. So the probability that xi equals 1. This is 1 minus p to the I. Right? If I receive packets 1, 2, 3, 4, 5, then I'll keep packet 5. If I lose any of them, I don't get packet 5. And that's true for any I instead of just 5. Right? So it's just so this sum is just I I is 1 to w of 1 minus p to the I, which is 1 minus p to the w plus 1, divided by 1 minus p, which is just p. And that would be a sum from 0 to w. I'm summing from 1 to w, so I just have to subtract that first term, which is just a 1, minus 1. Okay, and part B was much too hard. So instead I said compute an upper and a lower bound. Right? Let me think.
Read it?
Read the question. You want me to read the question?
No, you want me to?
No, I got it. Part B is each act is lost with probability P. Right, so there will be R rounds. So let R equal random variable that equals the number of rounds until the ACK is received. And let n equal a random variable that equals number of packets in the window. Received. Okay. E of R is just 1 over 1 minus P. Right? I mean, if P is 0, no loss, it's going to be 1. If P is 1, it's going to be infinite. And, that's just standard. You can have computed E of R to be the sum of the probabilities that R is greater than I, from I equals 0 to infinity. And it's just, the probability that R is greater than I is just the probability you don't get the first I acts. P to the I, right? And that sum equals that 1 over 1 minus P. Right? Okay. Even, I said n is too hard to compute exactly. Because, okay. If these are what are received in the 3 rounds, then the sequence you would keep is you would keep 1 and 2 from the first round, 3 from the second round, 4, 5, 6 from the third round. Right? Everybody sees that? I mean, the idea was you discard everything that you receive out of order. So I got 1 and 2, well, then I got 4, so I get rid of it. 4, 7, 9, I get rid of all those. Then I get 1, 3, that's what I need next. Then I get 5, I've missed 4, so I discard all those. And then next time I get 2, 3, and I keep 4, 5, 6 because that's what I was waiting for. Okay, so that would, with this sequence of arrivals, that's the sequence I would keep. For the upper bound, what we said is don't worry at the order in which they come in. After all those rounds, just take anything that you received where you also received all the packets prior. Right. So in this case, I've received by the end of these. Let's make this 10 instead of 9. Okay, by the end of this, I've received 1, 2, 3, 4, 5, 6, 7, 8, but not 9. So even though I received 10, I would discard 10. Okay, so if we did this exactly, I would receive 1 through 6. The upper bound in this case is receiving 1 through 8, and the lower bound, what I said was sort of take in each round, take the longest contiguous sequence that starts with 1. So this guy went 1, 2. This guy went 1, 3. 1 is longer than 1, 3. This guy started with 2. I don't even take that sequence. So the lower bound in this case would be 1, 2. The upper bound is 1, 2, 3, 4, 5, 6, 7, 8, and the actual 1, 2, 3, 4, 5, 6. Okay, so people see how we're choosing the upper and the lower bound. The upper bound is you look at everything and say, you mix them all up and say, what's the longest sequence that goes from 1 without a loop? And that's the upper bound. The lower bound is look at each one individually and how far can I get from one, to some number as a contiguous sequence, and I just take the max over all those. And that's a contiguous sequence that I'm going to keep. Okay. So let me do the random variable in one shot. So I'm going to define x of I comma r to be 1 if there are r rounds exactly and I want to do it. Yeah, if there are r rounds exactly and the I packet is received. Okay, and now what I want to compute is the sum r equals 1 to infinity, I equals 1 to w, all the xi's. I want e of xi comma r, or r comma I comma r. Right, that's what I want to compute. Right? And I can pull the sums out of the expectation. This is just going to be the sum r equals 1 to infinity, sum I equals 1 to w of e of xi comma r. Okay? So now, which of course is equal to the probability that x of I comma r equals 1. Right? Okay. So now for the upper bound. What's the probability that x of I comma r equals 1? Well, first of all, the first r minus 1 ACK had to get lost, and the last ACK had to be received. So that's just p to the r minus 1 times 1 minus p. That ensures that indeed only r rounds took place. And now I have to do it for my get this I right. So what's the probability that I get this I packet for the upper bound? Well, it was that in all these r rounds, over all these r rounds, I had to have received the first packet, the second packet, the third packet, and at least one of those rounds. Okay? So if I didn't get it in any rounds, I don't receive the packet. So let's see. I have, if I don't ever get it, then I fail. Yeah. Okay. That's a probability I don't get some packet in r rounds. Right? That's the probability that I do get the packet over those r rounds, and I have to make sure that I get all I packets. So this I have to have this happen I times. Right? That's the probability that I get the first and the second and the third and the fourth and the fifth and the sixth and the seventh and the eighth packet up to the ith packet, right? When I have r rounds to try and transmit each one. For the upper bound, I just have to make sure I get it at least once. Okay? And what about the lower bound? The lower bound, I need to have some sequence that goes from 1 up to I. Okay, so I get r chances to have this, to attempt this. Okay, so the only way it fails is if I don't get it every time. So it's going to be equal to 1 minus something to the rth power. And what I have in here is the probability that I attempt to get up to I packets, but I never succeed. Right? So I succeed if I get 1 minus p to the I. All of those I packets I'm waiting for in that sequence all come through. So 1 minus that is the probability that I fail. So I think that's the answer. Right? This is okay, I got a sequence of I packets in a row. This is I did not get a sequence of I packets in a row. This is that I did not get a sequence of I packets in a row R times, and this is at least once I got at least a sequence of I packets in a row. Which is how we state the lower bound. Yeah, Ron.
Consider the first term as an upper bound expression.
Sorry?
P to the R minus in the upper bound. What is that?
Why is this here? Oh, I'm sorry. I need this in both. And this also has to be times P to the R minus 1 times R minus P. This part has to do with the acknowledgement. The way I define the random variable, x of I, comma R. I said, 1, if R reaches, if there are R rounds exactly, and the I packet is received. Right, so this part ensures that there are exactly R rounds taking place. Because the first R minus 1 acknowledgments from the receiver get lost, and the last one gets through. So there are R minus 1 of those rounds, and given that, this is the conditional probability that given there are R rounds, that the way we computed the upper bound, the I packet is kept. Okay, same thing here. This is a conditional probability that given that there are R rounds, the way we compute the lower bound, the ith packet is kept. And it's just the probability that there are exactly R rounds. Okay, and then you take the sum, just apply this sum to these equations, and you can do some simplifying.
Is 1 minus all that to the R to the power all times the R?
Actually, it's this whole thing. Okay, and then the extra credit. Why is the answer going to be E of n over E of r and not E of over r? Because they're different, right? I mean, expected value, you can pull the sum out of the E. Huh? Oh, R over N. No, it's N over R. The expected number of packets. Oh. Why is the expected number of transmissions per round? That's the typo. It should be E of N over E of R. Huh? Oh, wait a minute. I'm sorry. I flipped the terms. The way I defined n in the problem, I called that r here, and what I called r in the problem, I called n here. So in the problem, n was the number of rounds, r was the number of packets received over all those rounds, and I just defined them the opposite way. So if I define them, I'm asking the right question here. And it makes more sense to define them this way. I don't know why I swapped them in the problem. Okay, but the important thing is if n is the number of rounds and r is the random, if n is the number of packets sent over, successfully delivered over those r rounds, and r is the number of rounds, y is the average number of packets sent per round equal to this and not equal to this. Okay, and let's see. Here's how you show this. If you were going to compute the average number of packets per round, okay, suppose you had 10 samples. Suppose you ran it 10 times. You had N1 and R1 up to N10 and R10. Or you did the experiment 10 times, right? How would you compute the average? What you would do is you would do N1 plus N2 plus N3 plus plus N10 over that, or would you do This one you don't divide by 2. Which of those two would you choose? Which one is the better average? Yeah, 10 samples. On the right-hand side? I actually prefer the one on the left-hand side. So why is the one on the left-hand side a better average? Well, okay, think of it this way. Think of it as a ball player or a soccer player, your favorite sport, right? This is pretty typical. The guy plays in his first year. He gets up at bat once. He gets 1 hit. Then the next year, he gets up at bat 1,000 times. He gets 20. Let's say he gets 0 hits. Okay. So, using this averaging mechanism, you would say he's got 1 plus 0 divided by 2. This is a 500 hitter. Not at all. Using the first averaging mechanism, he's gotten 1 hit out of 1,001 attempts. I don't care. I mean, make this something else. Make this like 45, right? I mean, still, under this averaging mechanism, you're treating the number of. It doesn't matter how many samples you have. You're giving them equal weight, right? So the point is, you sort of want to take the total number of samples you have. And take the total number, divide the number by the total number of samples. Right? That's a better averaging mechanism. Okay. It doesn't. This one has bias toward, the one with the fewer rounds gets a more heavily weighted bias. Okay. So once you can convince yourself of that, now I've got the sum of I equals 1 to j of ni over sum I equals 1 to j of ri, right? And let me do one other thing. Let me divide the top and the bottom by j. Right? I haven't changed anything. The j's outside of the sum. I divide the numerator by j and the denominator by j. Right? No change. And now let me take the limit as j goes to infinity of the numerator and the denominator. Well, the limit as j goes to infinity of a bunch of samples divided by the number of samples. That is E of n. And this is E of r. Right? I mean, what does it say? What does the expected value mean? The expected value means I take a bunch of samples, and sort of what's the average outcome. Right? That's exactly what we're doing here. Right? Number of take samples and divide by the number of times you took the sample. That's how you compute the average. So that's part C.
Would it have been sufficient to show that those two over there aren't the same? Or that one isn't as good?
That would have been. You should get some credit.
Or would you still need to show?
If you showed this was better than this, then I'd say, yeah, you sort of got halfway. And then you just need to sort of make the observation that if you take the limit of the numerator and the denominator, that's what gives you the e's. Okay. Your question?
For the upper bound, you express Px I r is equal to 1 in terms of
packets items on
Would that?
Did you express?
I mean, you'd have to do it recursively, but the recursive solution for the exact result is not that easy to come by.
for the exact result, we have to present this in
That's the only way. I mean, maybe there's a way to do it otherwise. That's the only way I know how to do it, and it's not even a nice recursion. It gets kind of messy. So. But you know, I thought about it for like an hour, and I trying to find a way to have a nice expression, and I couldn't figure it out. So that's not proof that it can't be done. But
Instead of the probability of x I equals to 1 equals to 1 minus t to half I.
Yeah.
Doesn't that expression meaning you receive I packets? And it doesn't prevent the cases you have some packets lost before I, say I'm at 2 I'm 3, and you get some package after I. So you need to specify you do receive from I to from 1 to I.
so the sender sends them in order, and there's no reordering.
So you receive
You receive them in order, but if packets get lost, and you don't. That's the only way the gaps can occur.
So you actually don't send all the W packets at the same time. You actually send 1, 2, 3, 4, 5.
I mean, yeah. If you send them at the same time, they still have to go out in some. I mean, they could all go out time. Yeah, they're not all sent at exactly the same time. There's still no such that there's an ordering. Right.
That you're gonna send like W packets at the same time, so you actually say you divide by the W to the I. Stuff like that.
Oh. Right. So I didn't explicitly say there's no reordering. No, so this is problem 2. I'm looking at problem 1. Oh, what packets that are received out of order are dropped by the receiver. So you could just treat an out of order packet as being dropped. And so that's if a packet comes out of order, and if it comes later in the sequence, then it should just treat that as lost. In which case, you know, again.
Like you send out W packets at the same time, then
I receive W at the same time also.
Right, and then you're saying you don't know what order they come in?
yeah.
So how would you solve the problem? I mean, you have to make some assumption.
So like for the I package you get started, I have to receive from 1 to I all the packages.
Right.
And they're and I have to use that expression divided by the omega W to the I. So make sure every one of them.
Oh, I see.
To make sure the I plus
1 is dropped. So I will set.
I see. You said every order is equally likely.
Yeah.
Okay. I mean, all right, the grader is going to make you wrong. If you really want to check the solution, I can look it over afterwards. But yeah, Sastra.
Time freeze for lands. Before we calculate the activity, each node calculates the least weighted path with a node.
First battery, yeah.
Node and it makes the interface which connects to the land takes to the root as part.
The one interface that takes it toward the root as R.
And so, assuming that from that land we have 2 other nodes. And only one of them is on the shortest path to the root.
Okay.
And what will happen if the other node is the one that has the lowest ID?
The way I described in class, the one with
ID number, the one that should keep the A's to the D on, and the other one should have it's off.
But I guess the homework solution doesn't reflect that.
The solution may not be the homework. It should. I went through several iterations with the guy. He kept making mistakes. But do you have it with you, or? Okay. I mean, that's the way it should be done. So he could have just. He made a mistake several times, and I told him, no, it'd be like this. So in the end, I thought we got it right, but I'll have to double check. I think for part, someone pointed out that for one of the later parts, there was an I guess it couldn't have been. There were two ways to construct the shortest path. So how you labeled your R's could have wound up being different, and that caused some confusion. But I thought all the D's were labeled correctly, but I'll have to look at it again. Patrick.
I just had a question. The Markov model and state machines. There's like the difference between the two of them.
So up until the only difference is really how you label the transitions, right? And what the states, and the Markov model is meant to be used in a stochastic framework, whereas the state machine is somehow meant in a deterministic framework. I mean the probabilities are assigned in the Markov model, but not in the state machine, right? So in a state machine, finite state machine, I have a state. I label this with some event in action, right? So a protocol designer would be more interested in this sort of specification. It tells them how their program should work, right? When this event happens, I want this action to be taken. And modelers would rather model it using a Markov model, right? Where I just say, there's some probability p or some rate lambda at which this transition is taken, which corresponds to the probability that when I'm in this state, this is the event that's going to occur.
So all the states are both present in both the Markov model.
Yeah. Right. It's the same problem, right? You have to create a state when that has to capture the information that you need to describe the rest of the process. So yeah, whatever you need to describe the process here, you probably want the same description here. I mean, it depends on what question you're asking here as well. Maybe sometimes different. It depends what you use as your set of events and what you want your states to represent. So if it may be the case that I have green and blue packets, and the queuing system behaves the same regardless. Like the packets are in the same flow, they have the same priority. But maybe I want you to specify when you get a green packet, do something. When you get a blue packet, do something. Then you can have a green edge and a blue edge. But for the most part, the same.
So you could have even probability. Decide to do that action. Basically, right? The probability of this transition happening is
Right. Yeah, right. Okay. You could find probabilities here as well. You could combine them. Yeah. Okay. Any other questions? Okay, so I'll question. Okay, I'll have homework 6 and 7. As soon as they're graded, I'll put them outside the lounge next to my office, and I'll send email about their availability. And homework 7 solutions, I'm going to meet with the TA now and try and get those up online as soon as he's made some corrections I want him to make. So the final is Wednesday. Yeah, Patrick? I'm not going to have any official office hours, but if people send me, are people? Okay, here's what I'll do. Monday, Tuesday, I'll be in my office from like 10 to 2, with a break for lunch. So if you can make it between 10 and 2, send me email and I'll pencil you in and make sure to be in my office at that time. But so I'll reserve 10 to 2 Monday and Tuesday to meet with students for with further questions. Okay.